What's up, you guys? It's Mel.
And Hiba.
This week's topic is Groovy Gravity.
Featuring our special guest, Isaac Newton.
Woo, let's give him a round of applause. The first topic we'll be diving into is the history of gravity. Now, our first question is, who discovered it? Well, the person who discovered gravity was Sir Isaac Newton. Newton proposed the idea in 1687 with his book called The Mathematical Principles, commonly known as the Principia. The next question we'll be discussing is, how did Sir Isaac Newton discover this? Well, when watching an apple fall, he thought about what gravity was. He believed that gravity was the attraction between two objects, as well as gravity not being dependent on the size of an object. While thinking about his beliefs, he discovered what gravity was. Our next question is, why is gravity important?
Gravity is important because without it, we would not be able to live on Earth and would just float away into space forever. With gravity, it keeps us a safe distance away from the sun.
The next question is, how do we use it?
Gravity keeps us on the ground, which allows us to put up buildings, homes, schools, and other things that we people use on a daily basis.
Our last question discussing the history of gravity is, what is gravity?
Gravity is the force that attracts a body towards the center of the Earth, or towards any other physical body that has mass.
As seen in the illustration, the Earth's center is what has a pull on the objects on its crust. This is how things stay grounded instead of constantly floating everywhere. Now that we've discussed the history of gravity and what gravity is, it's time to discuss how exactly we can find the magnitude of the force of gravity. We will do this by performing an apple drop demo. Are you ready? As the apple is dropped, the forces of gravity immediately take into effect. The apple is pulled towards the center of the Earth in a downwards motion. If gravitational force was not present, the apple would most likely float upwards due to the absence of the Earth's pull. Using the apple's fall, we can calculate the amount of force applied to it. But how, you may ask? We use a formula derived from Sir Isaac Newton's second law, F equals m times a. F is the total force, in this case, force of gravity, represented by F of g. M is the mass of an object, in this case, the mass of an apple. And A is the acceleration. Using the formula, we can plug in values determined through the demonstration to calculate the total magnitude of gravitational force. The determined mass of the apple was 5.972 times 10 to the 24 kilograms, multiplied by Earth's acceleration, 9.8, would get you a total value of 5.826 times 10 to the 25th newtons. We will now discuss how gravity is used on a bigger scale.
With advances in technology throughout history, we soon discovered that gravity is used on a much bigger scale than just apples falling to the ground.
A major example of how gravity is used on a much bigger scale is how it is used in our solar system. As we know, the Milky Way is a collection of planets and stars, in which the planets revolve around one big star, the Sun. Many people don't know, but gravity is what keeps our planets attracted to the Sun. The Sun, being the largest out of all our planets, has a strong gravitational pull on them. The force exerted by the Sun allows for it to have a pull that keeps planets such as Mercury, Venus, and Earth, and the rest of our solar system's planets circling around it. Now it is time to discuss other equations used in the process of determining the magnitude of gravitational force. The formula derived from Newton's second law, force equals mass times acceleration, is the most common formula, but what it lacks is the ability to incorporate other objects and their masses and take them into account. What should you do if you have two objects that are a certain distance apart and have different masses? You guessed it, use another equation. The equation used when determining the magnitude of gravitational force between two objects is F of g equals g times m1 times m2 over r to the power of 2. Unlike force equals mass times acceleration, the F of g times g m1 m2 over r to the power of 2 equation uses two more variables. F of g in this formula represents the magnitude of total gravitational force, similar to F in Newton's second law. G represents the universal gravitational constant, which has a total value of 6.67 times 10 to the negative 11th newtons times meter to the power of 2 kilogram to the power of negative 2. M1 represents the mass of one of the objects used, and M2 represents the mass of the second object used. R is a variable for distance between the two objects, measured in meters. A real-life example of this equation being used would be calculating the gravitational force between the Sun and the Earth. The Earth has a mass of 5.972 times 10 to the 24th kilograms, while the Sun has a mass of 1.989 times 10 to the 20th kilograms. The distance between the two planets is 149.6 billion meters. We would start by multiplying 6.674 times 10 to the negative 11th by the combined total of both masses, which is 1.187 times 10 to the 45th kilograms. The combined total of the numerator would be 7.928 times 10 to the 34th. The total distance, which is r squared, would be 2.238 times 10 to the 22nd meters. The total calculated gravitational force present in between the Sun and the Earth is 3.5 trillion newtons, or 3.5 times 10 to the 12th newtons.